Hello, my name is Luis, and for my advanced energy technology project, I actually chose to do nuclear fusion, specifically how it works, its history, where it is now, so things such as recent advancements and where it will be, so future projections and such. So how does nuclear fusion actually work? So as we all saw with nuclear fission, it's actually when scientists fire neutrons at really high speeds at atoms such as those of plutonium and uranium that are used in nuclear reactors. And this causes them to split and then release energy, which can then be harnessed as electricity and used for other purposes. However, nuclear fusion is kind of the opposite. It's when scientists fire um, two light nuclei. So specifically, they're using hydrogen isotopes right now, deuterium and tritium, and they're firing them at each other at very high speeds. And this all needs to occur in plasma. So they need to heat up the reactor very to very, very high temperatures essentially. And the reason that they're being fired at each other at really high speeds in the first place is because they're trying to overcome something known as the Coulomb force. And the Coulomb force is essentially a force that says that atoms with like charges tend to actually repel each other. So overcome they need to overcome this repulsion by being fired at each other at really high speeds. Oh, oops. So starting with the history of nuclear fusion, where does it actually come from, originate from, or where did the inspiration for it come from? And it actually came from an astrophysicist known as Arthur Eddington when he proposed that energies drew their energy from fusion of hydrogen into helium. And he actually published this paper in 1926, and this laid out the groundwork for nuclear fusion. So stars actually, or many stars, use nuclear fusion as the form in which they produce energy. So for most of their lives, they're repeatedly firing hydrogen isotopes and forming helium, which is releasing light and heat and producing energy. So moving on from that to 1934, and this is when Ernest Rutherford, a New Zealand physicist, a really famous one actually, performed an experiment that showed that the fusion of deuterium into helium actually released vast amounts of energy when fused. So, oops, skip the slide. So continue from that. So in the 1950s, Russian scientists actually proposed the idea for a magnetic confinement fusion device known as the tokamak, and I'll be talking more about tokamaks later on. But in 1977, the European government actually gave the thumbs up for the GET or the JET, or known as the Joint European Torus, since it's actually the largest, most advanced nuclear fusion device in the whole world. And it was completed in 1983. And in the same year, they were actually able to produce the first plasma in the jet, which is where fusion actually occurs. And actually, even now, or recently in the 1990s, which actually isn't so recent, 30 years ago, to the 2000s, and even a few weeks ago, they're actually breaking world records on how much energy can actually be produced from fusing these hydrogen isotopes and seeing how much energy they can actually harness. So moving on to some advantages of nuclear fusion. So starting off, there's no emissions or very, very, very little, and no nuclear waste, as we all saw with fission, that the half-life of plutonium or radioactive plutonium and uranium can actually last for hundreds of thousands of years, which poses a huge threat to future waste dealing or problems. There's also okay, so my computer actually turned off in the middle of my presentation, but moving on. So there's no risk of proliferation. So that means no terrorism can occur since they're not using radioactive materials such as plutonium and uranium that are actually used in bombs or nuclear bombs. And then there's no risk of chain reaction or meltdown since nuclear fusion devices actually cool down in seconds and there's no chain reaction to begin with. And then there's high energy density is another really big pro since it's proposed, or I guess theoretical, that 1 gram of deuterium can actually be used to produce 100,000 kilowatts of energy. And another thing is that it's abundancy and it's very inexpensive. So it's really abundant in the oceans, and scientists are actually extracting it from the ocean. It's specifically deuterium and tritium. And as far as inexpensive goes, it's proposed to cost around 3 cents per kilowatt hour, which is really, really cheap. And then this is also theoretical, but I guess relevant, and that's energy efficiency. And if done correctly, 1 kilogram of fusion fuel can actually produce uh, the same energy as 10 million kilograms of fossil fuels, which is really great since all those emissions aren't going to contribute to climate change. So what are some drawbacks and barriers? Obviously, there's a public perception problem. And like we all saw with Pandora's Promise, anything with nuclear attached to it is going to face public perception problems, since Fukushima and Chernobyl are still really big problems in the back of people's minds that are causing a lot of people not to support nuclear. But even though it's nuclear fusion versus fission, they're still going to attach nuclear to it. The industry still requires innovation, brain power, and it's still in the developmental phase. So it's also really, really expensive to build fusion devices. I think the GET in Oxford actually cost around 450 million to build. And on top of that, it's also really expensive to heat them up in order to reach the temperatures to reach plasma where fusion can actually occur. Otherwise, nothing's going to be occurring there. And then what are some unintended consequences that scientists are missing? Or are there any unintended consequences that scientists could be missing, since scientists tend to be optimistic? Is there anything that might be going over their heads or not paying enough attention to? Is there like a sort of like nuclear meltdown, but for fusion, I guess, like something that can occur that can be as catastrophic as hydros going wrong or nuclear reactors going wrong? And another really big thing or really big drawback is that energy input is actually largely outweighing energy output. So they're using a lot more energy to be able to put in energy to even get small amounts of energy outputs from nuclear fusion devices. So as far as implementation goes, it's still in the developmental phase, as mentioned, and there are actually several hundred around the world. So I think there's around like 250. So how can it actually be implemented worldwide? And do I believe it will be implemented in the future? I think it will be, and I think it could be one of the most powerful forms of energy in society. However, it still needs to overcome the public perception problem that's facing with nuclear. And on top of that, it needs to get the right amount of funding, the right amount of brain power from scientists, and yeah. So recent advancements. Actually, 2 weeks ago, the jet fusion device, the Joint European Towerist in the UK in Oxford, actually broke its own previous record of, I think it was set in 1997. And it broke its own record for the amount of energy that can actually be produced by squeezing two forms of hydrogen together. And as far as 21st century projections go, so there are actually projections of producing electricity about halfway through the century. So in the 2050s, which is still far, far away, but that's why the nuclear fusion is still facing the problem of the right amount of innovation and brain power that needs to go into in order for it to get to where it needs to be. And something else is that a new UK power plant design was actually proposed, and it's called the compact spherical tokamak, and it's set to deliver electric power output on the time scale of 2040. And then these are my sources.